Welcome back to another metrology and measurements session. Today we are going to discuss about the second unit, measurement of linear angular dimensions, assembly and transmission elements. My name is P.NAVIN JASS, Assistant Professor, Department of Mechanical Engineering, Rohini College of Engineering and Technology.
We are going to continue the session of gear measurement. In this gear measurement, we are going to discuss the new topic, spur gear measurement. Okay, in the next topic is spur gear measurement. So in this spur gear measurement, some of the inspections are made on the gears. So in this inspection, some of the following elements which we are found out in the manufacturing error, maybe it is present on the gears. By this method, the individual elements of the gear are to be checked in this process. So it is a slow and time-consuming process. Okay. So now we are going to see some of the errors which may occur or present in the inspection is run-out measurement, pitch measurement, profile measurement, lead measurement, backlash measurement, tooth thickness measurement, concentricity and alignment measurement. Okay. So first we are going to see about the run-out measurement. Run-out measurement. So what is meant by run-out measurement? So this is the example of run-out measurement. This run-out refers eccentricity in the pitch circle. This run-out refers eccentricity in the pitch circle. So it produces a periodic vibration during each revolution of the gear. So when each revolution of the gear, the vibration which may occurs on the process. So it results in tooth failure in gears. So it may result in the tooth failure or tooth break-in or tooth breakage in the gear. So run-out is measured by means of eccentricity tester, and the dial indicator of the tester is processed by the calibrated wire or a tip depending on the module of the gear, and the wires or tips inserted between two spaces. Okay, the gears are rotated tooth by tooth, and the variation is noted from the dial indicator. So the next one is pitch measurement. In pitch measurement, normally there are two different ways of pitch measurement. One is point-to-point measurement or tooth-to-tooth measurement, and another one is direct angular measurement. One is point-to-point measurement or tooth-to-tooth measurement, and another one is direct angular measurement. So this is the tooth-to-tooth measurement diagram or example of figure. So in this tooth-to-tooth measurement, it has three tips such as fixed measuring tip, sensitive tip, and adjustable tip or guide stop. So maybe it is a fixed measuring tip, sensitive tip, and adjustable or guide stop. So here is the fixed measuring tip or sensitive tip, and adjusting here there is a sensitive tip, and this is the adjustable or guide stop. So this again I am telling fixed measuring tip, adjustable or guide stop, and sensitive tip. So the position of the tip can be adjusted by a screw. The further movement of the sensitive tip is transmitted to the dial indicator through a leverage system. The adjustable stop is required for the stability of the instrument, and its position can also be adjusted by a screw. So this is the small working of the tooth-to-tooth measurement or point-to-point measurement. The next one is direct angular measurement. It is the simplest method for measuring the pitch error by using a set of dial gauges, by using some of the 2 or 3 dial gauges, we are going to check the pitch error against a tooth. So in this method, two measuring contact tips are applied on the same side of the adjacent teeth of the gear. So the left hand tip is first set to the required module by means of some suitable arrangement. The right hand tip is two arm lever. Among them, one contact the gear tooth and the other one actuates the contact point of the dial indicator. By this, we can able to find out the pitch measurement in this by using direct angular measurement. So the next one is profile checking. Next one is profile checking. In profile checking, there are two different types of profile checking are there. One is optical projection method and another one is involute measuring machine. One is optical projection method and another one is involute projection machine. So in optical projection method, the magnified profile of the gear is projected on the screen by an optical lens. Then the projected value is compared with the master profile. Already we studied in the metrology laboratory session about this profile projector. So this method is one of the example for the optical projection method. Okay, in that profile projector, we can able to get the profile checking of the screw thread or gear or anything. Okay, so with the help of this profile projector, we can able to find out the profile measurement and able to find out the error with the help of the master profile. Already we have a master profile which is to compare with the projected value in the profile projector. Okay, so the next one is involute measuring machine. Involute measuring machine. So this figure shows the one of the example for the involute measuring machine, and this is the example for the involute measuring machine. So in this method, the gear is held on a mantle for the measurement. Okay, the gear is held on a mantle for the measurement. A circular disc is having the same diameter. The circular disc is having the same diameter as the base of circle, and a test is fixed on the mantle along with the gear. Okay. So now after fixing the gear on the mantle, a straight edge of the instrument is brought in contact with the base circle of the disc. Now, if the gear along with the circular disc is rotated, the straight edge moves over the disc without slip. The stylus of the dial gauge is brought in contact with the tooth profile. When the gear disc are rotated further, the stylus slides along the involute curve. So the deviation of the profile from the correct involute is indicated by a dial indicator with the accuracy of 0.0001 mm. A master involute template is also provided with the machine setting and calibration of the machine. So the next one is the lead checking. It is checked by lead checking instruments. Lead is the axial advance of the helical or the worm thread per turn. The control of the thread lead is necessary to ensure an adequate contact across the face width. Lead is the axial advance of helix for one complete turn. The lead checking instruments advance a probe along a tooth surface parallel to the axis when the gear rotates. Then next one is backlash checking. In this backlash checking, there are two different types. One is circumferential backlash and another one is normal backlash. So the backlash is the distance through which a gear can be rotated to bring its non-working flank with the teeth of the mating gear. It is measured by mounting the gears in a specified position. So the numerical values of backlash are measured at the tightest point of the mesh on the pitch circle. So there are two different types of circumferential types of backlash. One is circumferential backlash and another one is normal backlash. The first one of the two gears of the pad is locked, while the other is rotated forward and backward, and the maximum displacement is measured by the comparator. So the stylus of a comparator is locked near the reference cylinder, and the tangent to this cylinder is called circular backlash. For precision gears, the variation should not exceed 0.02 to 0.03 mm. So the next one is tooth thickness measurement. Tooth thickness measurement. So here, by this method, we can able to measure the thickness of the gear tooth. Tooth thickness is generally measured at a pitch circle, and it is defined as the length of an. It is difficult to measure tooth thickness directly. So the caudal thickness measurement is carried out chord joining the intersection of the tooth profile with the pitch circle. The difference between the caudal tooth thickness and the circular tooth thickness is very small for gears of all or small pitch. So here we are used some of the measuring techniques of the gear tooth thickness. One is gear tooth vernier caliper, base tangent method, constant chord method, measurement over pins or box. Okay, the first one is gear tooth vernier caliper method. Gear tooth vernier caliper method. So this is the diagram for the gear tooth vernier caliper, and this is the process of gear tooth vernier caliper measurement. Okay, here that's the gear tooth. The gear tooth vernier caliper JASS are over the both sides of the gear tooth. Okay, so by this gear tooth vernier caliper method, the thickness can be conveniently measured by gear tooth vernier. Okay, so in this method, the thickness is measured at the pitch line. The thickness is measured at the pitch line as shown in this diagram. The gear tooth thickness varies from the tip of the base circle of the tooth. The instrument must be capable of measuring the tooth thickness at a specified position on the tooth. First, we should know about what is gear tooth thickness and what are the parts of the gear tooth thickness. This gear tooth vernier caliper. What are the parts of the gear tooth vernier caliper? And this gear tooth vernier caliper has two vernier scales. One is on the vertical position and another one is on the horizontal position. Okay, the vernier scale is used to set the depth along the pitch circle from the top surface of the tooth at which the width has to be measured. The vertical vernier scale gives the caudal addendum. The horizontal vernier scale is used to measure the caudal width of the teeth. Okay, here now we are going to considering one gear tooth. The theoretical values of W and D can be found or which may be verified by the instrument. It may be noted W is the chord ADB as we saw in this figure. W is the chord ADB. Okay, so but tooth thickness is specified as an arc distance AEB. So here W is a chord ADB, W is a chord ADB, and tooth thickness is specified as an arc distance AEB. AEB. The distance D is adjusted on the instrument. The distance D is adjusted on the instrument is slightly greater than the addendum CE. So D is slightly greater than the addendum CE. Okay. So W is therefore called as caudal thickness. So we call this W as a caudal thickness, and D is called as caudal addendum. W is called as caudal thickness and D is called as caudal addendum. So as we saw in the figure, W is equal to AB is equal to 2 into AD. We are taking W is equal to AB or 2 into AD. That we are taking, once again I am telling W is equal to AB, A into B, or which is equal to 2 into AD. AOD is equal to theta, which is equal to 360 divided by 4n, where n is here, n is nothing but number of teeth. So W is equal to 2 into AD, which is equal to 2 into AO sine theta, which is equal to 2 into R into sine 360 divided by 4n. 2 into R into sine 360 divided by 4n. R is nothing but it is a pitch circle radius. So module M is equal to, we know PCT divided by number of teeth, which is equal to 2R divided by N. That is R is equal to NM, number of teeth into module divided by 2. Or radius is equal to number of teeth into module divided by 2. So W is equal to 2 into number of teeth into module divided by 2 into sine 360 divided by 4n. So NM is equal NM into sine 90 divided by N. So from the figure, D is equal to OC minus OD. We are taking D is equal to OC, into C minus O into D. Here OC is equal to O into E plus addendum. Here OC is equal to O into E plus addendum, which is equal to R plus M, which is equal to NM, number of teeth into module divided by 2 plus module. So OD is equal to R into cos theta, NM divided by 2 into cos 90 divided by N. So D is equal to Nm divided by 2 plus M minus Nm divided by 2 into cos 90 divided by N, which is equal to Nm divided by 2 into 1 plus 2 divided by N minus cos 90 divided by N. So here any error in the outside of the gear must be allowed for when measuring tooth thickness. So in the case of helical gears, the above expressions have to be modified to take into the account change in curvature along the pitch line. The virtual number of teeth NB for helical gear is equal to N by cos cube alpha. So alpha is nothing but here we are taking as an helix angle. So from the above equations, N can be replaced by N by cos cube alpha and M by Mn, which is called as the normal module. So some of the disadvantages in this gear tooth vernier method, it is not closer to 0.05 mm. Two vernier readings are required. Measurement is done by edge of measuring jar and not by face. It needs a different setting for the variation number of teeth for a given pitch. Accuracy is limited by the least count of the instrument. So these are the disadvantages of the gear tooth vernier caliper. Now the next one is gear tooth thickness measured by the constant chord method. Constant chord method. So in this gear tooth vernier caliper, by using constant chord method, both the caudal thickness and caudal addendum are dependent upon the number of teeth. Here, for measuring large number of gears for set, each having different number of teeth would involve separate calculations. So the procedure becomes laborious and time consuming one. So we need more time for this type of calculations by using constant chord method. So this constant chord method does away with these difficulties. This method is measured where the tooth flank touch the flanks of the basic rack. The teeth of the rack are straight and inclined to their central lines at the pressure angle. So the constant chord of a gear is measured where the tooth flanks touch the flanks of the basic rack. The teeth of the rack are straight and inclined to the central lines of the pressure angle. When the gear is rotated and all teeth are come in contact with the rack, then for given size of a tooth, the contact always takes place at point A and point B. The distance AB remains constant. So it is called as a constant chord. So here now we are taking, since the gear tooth and the rack space are in contact in the symmetrical position at the points of contact of the flanks, the chord is constant at this position irrespective of the gear of the system in mesh with the rack. So this is the property utilized in the constant chord method of the gear measurement. So here AB is known as the constant chord. Constant chord is defined as the chord joining points, those points are opposite faces of the tooth which make contact with mating teeth when the center line of the tooth lies on the line of the gear centers. The value of AB and its depth from the tip where it occurs can be calculated mathematically and then verified by an instrument. The advantage of the constant chord method is that for all the number of tooth, value of the constant chord is same. The value of the constant chord is constant for all gears of a machine system. It readily lends to a form of comparator which is more sensitive than the gear tooth vernier. From the figure, we are taking PD is equal to PF. PD is equal to PF. Okay, PD is equal to PF, which is equal to arc of PF. Arc of PF, which is equal to 1 by 4 into circular pitch. We know circular pitch is equal to pitch circle diameter PCD into pi divided by number of tooth. So 1 by 4 into pi into PCD divided by m. So 1 by 4 into pi into m. Since module we are taking PCD divided by m. So 1 by 4 into pi into m. Since line AP is in the line of action, it is tangential to the base circle. So angle of CAP is equal to psi. The right angle triangle APD is equal to APD. AP is equal to PD. The right angle APD. The right angle APD is equal to AP is equal to PD into cos psi, which is equal to pi by 4 into m into cos psi. So in triangle PAC, AC is equal to AP cos psi, pi by 4 into m cos squared psi. C is equal to constant chord, which is equal to 2AC is equal to pi by 2 into mn cos squared psi n. Therefore, mn is equal to normal module. Module of the cutter used and psi n is equal to normal pressure angle. So PC is equal to AP sin psi, which is equal to pi by 4 into m into cos psi into sin psi. So D is equal to addendum minus PC. D is equal to addendum minus PC, which is equal to m minus pi by 4 into m cos psi sin psi is equal to m into 1 minus pi by 4 cos psi sin psi. So for helical gear, D is equal to mn into 1 minus pi by 4 into cos psi n sin psi n. Therefore, height of AB above the pitch line is equal to PC is equal to pi m divided by 4 cos psi sin psi, which is equal to pi m divided by 8 sin 2 psi. So the next one is gear tooth thickness measurement by base tangent method and David Brown tangent comparator or David Brown tangent comparator. So it is the most commonly used for checking the tooth thickness of gear. The advantage of this method is that reading depends only one vernier reading, unlike gear tooth vernier caliper where two vernier readings are recorded. So comparatively, it is best with the gear tooth vernier caliper. A span of convenient number of teeth is measured with the help of the tangent comparator. Here, single vernier caliper has the following advantages over gear tooth vernier, which is used to vernier scales. One is the measurement do not depend on two vernier readings. Second one is measurement is not made with an edge of measuring jar. with the face. Okay, then its ends sweep out opposed in involutes A2 AA1 and C2 CC1. The measurements made across these opposed involutes by span gauging will be constant. So that is AC is equal to A1 C1, which is equal to A2 C2 and A0 C0. The base tangent length consists of one base circular thickness of tooth and number of base pitches. So base tangent is equal to one base circular thickness plus one number of base pitches. Number of base pitches. So here we are going to use the base tangent method. Now let us consider that the gear has got W number of teeth. W number of teeth and AC on pitch circle corresponds to S number of teeth. This gear got W number of teeth and AC got pitch circle to responds to the S number of teeth. Therefore, distance AC is equal to S minus 1 by 2 pitches. Angle subtended by AC is equal to S minus 1 by 2 into 2 pi by n radians. Therefore, angles of arcs BE and BD, involute function of pressure angle psi is equal to tan phi minus phi. Angle of arc BD is equal to S minus 1 by 2 into 2 pi by n plus 2 into tan phi minus phi. BD is equal to angle of arc BD into R into RB. Therefore, BD is equal to S minus 1 by 2 into 2 pi by n plus 2 into tan phi minus phi into RP cos phi, because here we are taking instead of RB is equal to RP cos phi. So M into N, module into number of teeth divided by 2 cos phi is into S minus 1 by 2 into 2 pi by n plus 2 into tan phi minus phi. Here we are taking instead of RP, we are taking Mn divided by 2. Okay. So now Nm into cos phi into pi s divided by n minus pi by 2n plus tan phi by minus phi. So we already defined length of arc BD is equal to distance between two opposed involutes. So n, which is equal to nm into cos phi into tan phi minus pi by 2n plus pi s divided by n. So here the backlash allowance is specified normal to the tooth flanks. This must be simply subtracted from this derived value. The distance is calculated and then set in the David Brown tangent comparator with the help of slip gauges. So the instrument essentially consists of a fixed anvil and a movable anvil. There's a micrometer on the moving anvil side, and this has a very limited movement on either side of the setting. So the distance is adjusted by setting the fixed anvil at dissect place with the help of looking ring and setting tubes. So the next one is measurement over rolls or balls. Measurement over rolls or balls. So here simply we are telling very clearly a very good and convenient method is for measuring thickness of gear. In this method, 2 or 3 different size rollers are used to check the vibrations at place on the tooth. Here, measurement over the rollers placed in the space between a pair of gear teeth gives a convenient method for checking tooth spacing and pitch diameter. 2 or 3 different size rollers are used to check the variations at several places on the tooth. Okay, so the next one is measurement of concentricity. Measurement of concentricity. The center about in which the gear is mounted should be coincident with the center from which the gear is generated. So it is easy to check the concentricity of the gear by mounting the gear between centers and measuring the variation in height of a roller placed between the successive teeth. The variation reading will be a function of the eccentricity which is present. And the last one is alignment checking. This alignment checking is done by placing a parallel bar between the gear teeth and the gear being mounted between the centers. The readings are taken at the two ends of the bar, and difference in the reading is the misalignment. Okay, so if we find out any difference between the readings on the both the ends, that is the misalignment of the particular gear. So the last topic today is Parkinson gear tester. Parkinson gear tester. This Parkinson gear tester. So this is the diagram for the Parkinson gear tester. In this Parkinson gear tester machine or roller gear tester machine, a standard gear which is called as master gear. This is the master gear, and that is an standard gear is called as the master gear is mounted on the vertical member. The gear under test is mounted on a similar mandrel. So here is similar mandrel which is mounted on the sliding movable garage. So there are two different mandrels are there. One is for the fixed mandrel, another one is in a sliding gear carriage, is fixed with the sliding gear carriage. So one is called as a master gear, which is fixed with the fixed mandrel, and another one is a gear under test, which is movable forward and reverse with the help of the garage. Okay. So the next one is the gears are in mesh due to spring pressure. These gears are arranged in such a way that they are free to rotate without any clearance. The right mandrel can be moved along the table and clamped at any desired position. The left mandrel slide against the pressure, and it has a limited movement. The two spindles can be adjusted so that the axial distance is very equal. So the dial indicator on the mandrel on the Parkinson testing machine, which is to show the errors which is occurs on the gear testing gear. So when the gear rotates, the movements of the sliding garages are indicated by dial indicator, and these variations are measure of any irregularities in the gear under the test. The variation can be recorded in a recorder which is fitted in the form of a waxed circular chart. So these are the waxed circular charts. It shows the reproduction of a few typical charts with a reduced scale and the radial errors magnified about 50 times. So the chart recorded by this test do not give a clear indication of true cumulative pitch error. It gives only composite error. This test is useful test for accepting or rejecting a gear, but it is not for finding out the detailed causes of the rejection. So if it is unsatisfactory, it is compulsory rejection. If it is a moderate, if it is in moderate, the chart is in moderate, maybe it is considered or rejected. But if it is in the full satisfactory, it is not rejected. It may be used for the further purpose. So some of the limitations of this Parkinson gear tester is it is directly dependent upon the master gear or reference gear. Measurement is directly dependent upon the master gear or the reference gear. So here the maximum gear diameter which is used to check here is 300 mm. And the accuracy is maybe plus or minus 0.001 mm. Here we can't able to identify the errors very clearly. The measurement is dependent on the low friction in the movement of the floating garage. So these are the limitations of the Parkinson gear tester. So by this this session is over. We are going to study the more topics in the upcoming sessions. Thank you.